In this video, we are going to discuss the MOSFET as an amplifier, and we are going to use the graphical analysis just to explain how the MOSFET can work as an amplifier, similar to what we did with the bipolar junction transistor. Before we start, we are going to stick to the same notations that we used with the bipolar junction transistor. For example, in order to use the MOSFET as an amplifier, we need to bias the amplifier using a certain DC bias point, and then we add our AC signal, or the signal to be amplified, superimposed on the DC. So we'll have in our circuit, we'll have DC, we'll have AC, and sometimes we'll need to use the total signal. So in order to discriminate between these notations, for the DC we are going to use all capital letters. So for the DC we use all capital letters and capital subscripts. For example, we say V, capital V, DS, capital I, DS, capital V, GS. This is for the DC. For the AC, we are going to use all small letters and small subscripts. So we say small v, small d, small s, small I, small d, small s, small v, small g, small s. For the total, which is the DC plus the AC, we will use small letter for the voltage or the current with capital subscript. So we are going to use small v but capital DS, small v but capital GS, small I but capital DS. So this is with respect to the notation that we are going to use, and just to not to get confused later. Okay? So in order to graphically explain how the MOSFET can work as an amplifier, let's consider a very simple circuit which consists of a MOSFET transistor, enhancement NMOS, and resistor, supply VDD, and then we are going to connect our voltage here, a DC voltage here, let's call it capital V, capital GS, to the gate of the transistor. The source of the transistor is connected to the ground, and this is considered now as our input, and the output of this circuit is taken at the drain. So the output is equal to VDS basically, and the input is equal to VGS. So the input voltage is equal to the voltage VGS, and the output voltage is equal to the voltage VDS. And I'm using here small letter with capital subscripts, which means that I'm talking about the total. But so far I have only DC. I will start only with connecting DC supplies. But keep in mind that the output is equal to the VDS, the total VDS here, whether it's DC only or DC plus AC. Same here, the input is equal to the VGS, whether this VGS is like DC only or DC plus AC. Let's start with having only DC sources. So we have only VDD and VGS. Remember that the relation between the current IDS, and VDS, from the physics of the transistor, we used to get many curves in this relation. The first curve was when VGS is less than V threshold, the transistor is off. So this curve with zero current when the VGS is less than V threshold, right? So the transistor was off and the current was zero. And then as you increase VGS, you start to get curves like this with saturation region and triode region. So as you increase VGS, let's say here this is VGS equals 2 volt, this is VGS, and let's talk about the total in general. So small v, capital GS equals 3. For example, I'm giving just these numbers for example. And so on. So you will get a set of curves that look like this. So this is from the physics, this set of curves, they come from the physics of the transistor, right? Let's go back to the circuit. From the circuit, we can find another relation between IDS and VDS. And this relation that we can find from the circuit, it comes from Kirchhoff voltage law. for example, we can say that if we consider this loop between the drain and source, we can say that the voltage VDD equals the output, which is VDS, plus the drop across this resistor, IDS RD, right? And from here we can get another relation between IDS and VDS. We can say that IDS equals VDD minus VDS over RD. This is another relation from KVL, from Kirchhoff voltage law, at the drain source loop. We can get this relation, which is a linear relation. This is a linear relation. We need only 2 points in order to plot this relation, and the two easy points that we can get are, if you put VDS equals VDD, you will get a point here, because the current will be 0. If you put VDS equals VDD, the current will be 0, so the current is 0 when VDS equals VDD. And the second point is, if VDS equals 0, then the current will be VDD over RD. So if VDS equals 0, then we'll get a point here with the current equals VDD over RD, and then we can connect these 2 points, and this will give us a line. This line is a relation that must be satisfied between IDS and VDS. It must be satisfied because it represents Kirchhoff voltage law. So this relation between IDS and VDS must be satisfied, and also this set of curves must be satisfied, depending on which VGS you are using. Okay? So from this relation, from these relations, from the physics of the transistor and the KVL, let's now think about plotting a relation between the input and the output of the transistor. The input of the transistor is the same as VGS, right? Which is the same as VGS. And the output of the transistor here is the same as VDS. Let's try to plot this relation between the input and the. First, when VGS is lower than V threshold, if VGS is smaller than V threshold, what happens? So let's take V input or VGS smaller than V threshold. If VGS is smaller than V threshold, then this will be the active curve, and the current, the operating point, will be here, which is the intersection of the line with the curve, intersection of KVL with the curve that represents the physics of the transistor. When VGS is less than V threshold, the operating point will be this point, which means that the transistor will be off and the current will be 0. And what else? The output, which is VDS, will be exactly VDD. So when VGS is less than V threshold, the operating point will be the output equals VDD. And then as you increase VGS, when you increase VGS above V threshold, what will happen is, the operating point will start to change from here to here, which means that the output voltage will start to decrease from VDD to a certain value. And then when you increase VGS again, the operating point will move to here, which means that the output will decrease again. And then you increase VGS. As you increase VGS, the output decreases again. In which region we are working here? In which region these operating points or these DC operating points are? These operating points are now in the saturation region, right? So the intersection here, the intersection or these operating points will be in that saturation region. And what happens as we increase VGS? What happens is the output is going to decrease quickly. As you see, it's going to decrease quickly. So as VGS increases above as VGS increases above V threshold, the operating point will enter the saturation region. Here, the operating point was off when VGS was lower than V threshold. When VGS was lower than V threshold, the transistor was off. And then as you increase VGS, the operating point will enter the saturation region of the transistor. And as you see, as you increase VGS, the output VDS is going to decrease. It's going to decrease quickly, right? So you will see that starting from this point, the output is going to decrease quickly. And in this region, the transistor will be saturation. Until you reach to a certain value when you increase VGS very much, and then the operating point will start to move to the triode region. So as you increase VGS, after a certain point, the transistor will enter the triode region. And when it enters the triode region, as you see from here, the decrease in the output will start to saturate. The decrease in the output will start to be very small. It will decrease, but it will not decrease very much. So as you increase VGS more, there is a decrease in the output, there is a decrease in VDS, but the decrease will be very limited, which means that you will find that the curve here, the decrease in the output, will be something like this. It will start to be saturated or limited. It will not decrease linearly as in the saturation region. It will start to decrease with a limited amount until it will reach to a certain value, and it will stop decreasing. It will reach to a certain value and it will stop decreasing. The output will stop decreasing anymore. Even if you increase VGS more, that's it. The output will be approximately the same value. And this is what we call the triode region. So this is basically the relation between the input VGS and the output VDS of this circuit. In the beginning, when VGS was very small, the transistor was off and the output was VDD. And then as you increase VGS, the operating point starts to move here, and we enter the saturation region, and the output decreases quickly. Until we reach, if you increase VGS more, we reach to the triode region. The operating point will move to the triode region, where the decrease of the output will be very limited, and this is now the curve between the input and the output of our circuit. So now imagine that we have a certain VGS that operates you, or it causes the operating point to be here in the middle of the saturation region. So let's assume that this is our DC value of VGS. Our DC value of VGS, it will cause the operating point to be in the middle of the saturation region. Let's take it like this. So our DC value of VGS, let's assume it's here. Now, in the middle of the saturation region, this is our DC value, capital G, capital V, capital G, capital S. This is our DC operating point. And now, let's inject our AC signal superimposed on this VGS. So let's here add our AC signal, and we are going to call it V, small g, small s. So we are going to inject our AC signal superimposed above VGS. So what happens now is the input now is it's not a DC signal only, it's a DC signal plus an AC signal. So the input is going to change around, this DC value. So if we assume that the input is going to change like this, and I'm going to plot it with another color. If the input changes like this, with a small change, and again small change because we want the input to see a linear part of the curve. Okay, so we need our input signal to be small, our input AC signal to be small. That's why our input AC signal, we call it the small signal. So when our input AC signal changes with a small change, this will cause the output to change around its DC value with a large change. And as you see, because of the slope of this line, small change in the horizontal x will cause large change in the vertical x, and here the amplification comes. Because you have an input as a small signal while the output became a large signal. This is because the slope of this line is steep, it has a high slope, and it will cause small input. The small input will cause large change in the output. However, you need to choose, in order for this to happen, you need to choose your operating point in the middle of the saturation region. So here, your DC bias point needs to be in the middle of the saturation region. So that first, you will benefit from the gain of this line, okay? And small change here will convert into large changes in the output. Second is the second reason to choose it in the middle of the saturation region. Actually, I forgot the second reason here. So, anyways, you need to choose the operating point in the middle of the saturation region in order to benefit from the slope of this line and benefit from the high gain of this line. Small change will give you high change. The second thing, it's not the second reason, the second point is you need the input to be small. Why? Because you need the input to see a linear part. Why do you need the input to see a linear part of the curve? Because we need to design a linear amplifier. Always we need the amplifier to be linear so that it doesn't distort your input signal. The output signal will be the same as the input signal. So the first thing, you need to choose your operating point in the middle of the saturation region, okay, in order to benefit from the gain. The second point is your input signal must be small so that it sees a linear part of your line. This is not a line, in fact, this is not a line, this is a curve. But you need to see like a linear part of the curve or a small part of the curve will be approximated as a line. Okay, so this is how graphically how the amplification happens in the MOSFET. Okay? The point is, you cannot choose the operating point close to the triode region and you cannot choose it close to the off region. So you cannot choose your operating point, your DC operating point here. Why? Because if you choose your DC operating point here, the output will be limited to VDD. The output cannot increase above VDD, right? So your output will be clipped. So the output will be amplified from one side. The output will be amplified. So if you choose your operating point here and you inject, for example, you inject your input signal like this. Okay? What happens is your output signal will be amplified from this side, but from the other side it will be clipped. Why it will be clipped? Because the output cannot increase above VDD. So this will clip your output, it will cause a distortion to your signal. So you cannot choose your operating point in the saturation region close to the off. You cannot choose it close to the off. And also you cannot choose it close to the triode, because if you choose it close to the triode, then again, it will be distorted because here it will not be linear. The relation will not be linear. So if you inject your input signal here, if you inject your input signal like this, what will happen is this part will be linear, so it will give you a sinusoidal shape. But this part of the curve will not be linear, which will cause your signal to be distorted from the other side. Okay? So basically, so here when the input decreases, it will cause let's say that when the input decreases, it will cause this will be a sinusoidal wave. Okay, because we have a linear part here, but from the other side, when the input increases, On the input increase, it will cause a distorted signal to appear at this. So you cannot choose the operating point to be close to the off or close to the triode. You have to choose your operating point in the middle of the saturation region in order for your amplifier to work properly, in order for your signal not to be distorted. Okay? The second point, I repeat again, is that your input signal must be small in order to see a linear part of the curve, and hence you have a linear amplifier. So that's it with respect to the amplification. Let's continue with the remaining topics in the next video.